Hello, we're gonna review Bayesian probability briefly. There were some students that requested a video on this topic. Well, basically what you have is you have two events, event A and event B, that are somehow related to each other. In other words, the intersection between the two events is non-empty. And as an example, let's say you have an event A that is a game, a soccer game, let's say, being canceled, and B is the probability of rain, right? So the question is, what is the probability of the game being canceled given that it's rain, right? Then you can clearly see how the rain can affect the game because the games are played outside. But let's say now you are wondering what is the probability of rain given that the game is canceled. In a way, you can see how they are related, right? Because you can still say, well, if the game is canceled, it may be a chance it was because of rain, and then therefore may be raining. And that's true. But then when you go to try to make the case, well, rain influences the games. That's clear. Like if it rains, then the games get canceled. But then you go back and say, well, then games being canceled influences the rain, and that is not true at all, right? So then is when things get iffy, and when people then make an argument for Bayesian not being real, or not being grounded on solid fundamentals. But as an advisor of mine used to say, everybody is an either Bayesian until you have no other choice. Because what happens is you may be confronted with a case in which you have B given A, but you have no way to be able to calculate A given B. And in that case, this may be your only choice. In that way, it's very hard to be a purist when you have no other choice. So with that said, it's up to you to make your decision if you believe it or not believe it, or if you like it or not like it. That's up to you. Anyway, now let's get a more practical example. Let's say you have some population, some sample, some population, let's say from a hospital. And in that hospital, you have heavy drinkers with a frequency of 30%, about 20% have liver disease. And when you look only at the patients that have liver disease, about 45% of those patients have liver disease. So they have liver disease and they're heavy drinkers. I mean, when you only look at the patients that have liver disease, 45% of them are heavy drinkers. And now you ask the question, well, in this population, what is the probability of getting liver disease given that you're a heavy drinker, right? So in that case, you can apply the Bayesian probability, and then the Bayesian probability is the probability of A given B is equal to the probability of B given A times the probability of A over the probability of B. Then you can just replace those by, well, what is the probability of getting liver disease if you're a heavy drinker? And then is the probability of being a drinker if you have liver disease times the probability of having liver disease, or the probability of being a drinker, and then just plug in the numbers, right? So and actually when you look at it, it's pretty straightforward. So the challenges of Bayesian probability are not so much plugging in the numbers. As you can see, plugging in the numbers is pretty straightforward. The challenge is more, well, in what cases it's clear that one event influences the other, but the other doesn't influence the first event, and what choices you can make to make certain you are applying in the correct scenario. So please let me know if this video was helpful, and if you have any other suggestions. Thank you.